You know, when you sent over those notes about matter,
Yeah.
it really got me thinking, like, what if the way we've always pictured, like, those tiny building blocks, those particles,
Right.
is actually, like, holding us back from truly understanding it?
Absolutely. And, your sources really hit on something there.
Yeah.
Especially that research from the Journal of Research and Science Teaching.
Okay.
It really highlights how those ideas we have
Right.
about solids, liquids, and gases
Yeah.
might actually be more of an obstacle
Okay.
than a starting point when we really want to grasp particle theory.
Yeah, exactly. And this paper, this is from 2010, right?
That's right, 2010.
It puts forward this whole different way of looking at it.
Yeah.
One that focuses on this concept of substance as like the real key to understanding it all.
Exactly.
So our mission today is to kind of explore this different framework with you.
I like it.
We're going to unpack why that standard model, that solids, liquids, gases thing that we all learned, might actually be causing some like fundamental confusion.
Right.
And how this substance-first approach could be like a real aha moment.
Totally. And let's be honest, the traditional way particle theory is taught, it can feel very abstract.
Yeah.
You're told everything's made up of these tiny particles.
Yeah.
But like, what does that actually mean for a piece of wood versus a glass of water?
It's like, okay.
It's no wonder so many people end up with a hazy understanding.
Totally. Okay. So let's dive into that hazy picture then.
Okay, let's do it.
The classic way we learn about particles usually starts with this pretty simple division of matter into solids, liquids, and gases.
Right. And the research you found makes a really strong argument that this first step might actually be a huge roadblock to really understanding what's going on at the particle level.
Interesting.
And it's fascinating how this seemingly obvious starting point leads us down some pretty misleading paths.
Okay, so what is one of those misleading paths?
Well, one of the first things they point out is this really vague identity of these particles that we're supposed to be learning about.
Yeah, like what are they?
Exactly.
It's like matter is made of particles, but
the standard model just throws out there matter is made of particles.
Yeah.
But it hardly ever clarifies what those particles are in relation to different materials.
Yeah. Are the particles in this table the same as the particles in the air?
Yeah. Are we talking about the same fundamental particle when we look at a wooden desk versus the air we breathe or the sugar in our coffee?
It's like, what are we even talking about?
Right. And that's where the idea of substance becomes super important.
Okay.
So by not directly linking these fundamental particles to specific pure substances, we blur this really crucial distinction between a single consistent material and like a mixture of different materials. Yeah. It's like trying to understand recipes by just saying food exists.
Right. Without ever specifying the actual ingredients for a particular dish.
I like that.
It gets even trickier.
Okay. How so?
Well, this solid liquids gases categorization can actually accidentally lead to this idea.
What's that?
That these are three completely separate kinds of matter.
Like different.
Almost like they're different fundamental ingredients of the universe.
Okay.
Right.
So instead of understanding that a single substance, like water,
like the water you drink,
can exist
and be solid, ice, liquid water, or gaseous steam, water color,
depending on the condition,
temperature and pressure.
Right. People start to think of solid stuff, liquid stuff, and gas stuff.
As like different things.
As different entities.
Wow.
And this isn't just an idea.
Yeah.
There was a survey done of over 5,500 students in England between the ages of 11 and 14.
Okay.
And a surprising number of them actually had this 3 types of matter misconception.
That's huge.
Yeah. So that really highlights how ingrained this framework can become.
Wow. So the very first thing we learn can actually set us up.
Unfortunately, yes.
For a fundamental misunderstanding.
Exactly.
Wow. Okay. So here's where it gets really interesting, for me at least.
Okay.
And this is something you mentioned in your notes too.
Yeah.
The standard model also has a hard time explaining everyday things like boiling and evaporation.
It really does.
We all know that water evaporates from a puddle.
Right.
Even when it's not 100 degrees Celsius.
Right.
So why is that?
This is a great example of where the traditional framework breaks down.
Okay.
It usually explains boiling as particles gaining enough energy to break free
okay.
and form gas bubbles within the liquid.
Right.
But evaporation happens at much lower temperatures.
Yeah. So where's the energy coming from?
Exactly. Where does that energy come from?
Right.
And if particles can just escape into a gaseous state, why doesn't all the water on Earth just evaporate away?
That's a great point.
Right.
The standard model just
kind of glosses over the surrounding environment, the role of the air above the water, and the fact that energy isn't evenly distributed among all the water particles.
Some are more energetic than others.
Exactly. Some will naturally have more energy than others.
Yeah.
And get this.
What's that?
Research has shown that even chemical engineering undergrads, people who deal with these concepts all the time, struggle with the idea that evaporation requires a temperature gradient.
So it's not as simple as
it's not just
water turns into gas.
Water turns into gas.
Yeah.
There's more to it.
So that brings up a question.
Yeah.
If this traditional way of teaching particle theory has all these problems, is there a better way?
And the research you shared strongly suggests that there is a framework that's centered around the concept of substance.
Okay, so instead of focusing on solids, liquids, and gases, we start with a pure substance.
Exactly.
Can you tell me more about why that's so important?
So what's really interesting here is that this idea of a substance, a pure material with consistent properties, is a cornerstone of modern chemistry.
Really?
Yeah, it really became a key concept back in the 18th century.
Wow.
And the research you shared even has a concept map that visually shows how we understand matter.
Okay.
And substance is right at the center of it.
It's like the key ingredient.
Exactly. It's like establishing what the fundamental stuff is before we even start looking at its different forms.
It's like saying this is gold.
Exactly.
And it can be melted or it can be solid.
Right.
Rather than thinking of them as two totally different things.
Yeah, like solid gold versus liquid gold.
Yeah.
Two separate categories.
Now, you mentioned a difference between the particles of a substance and atoms. What did you mean?
So while atoms are the building blocks of all matter, they're not necessarily substances themselves in the way we're talking about, for example.
Yeah.
Oxygen atoms can combine to form oxygen gas, which is O2.
Right.
And they can also combine in a different way to form ozone, are two totally different substances.
With different properties.
Exactly, with different properties.
But a single oxygen atom is not oxygen gas and it's not ozone.
Exactly.
Okay, so this framework helps us distinguish between like the pure material and like
and the deeper level.
The atoms that make it up.
Of its atomic makeup.
Okay, so we're putting substance at the center of it all.
Yes.
What are the like key principles then of this substance-based model?
Okay, so the first key principle is to make a clear difference between pure substances and mixtures.
Okay.
And a good way to do this, especially for younger learners, is by looking at melting.
Okay.
So pure substances have a very specific fixed melting point.
Okay.
Like pure wax melts at 64 degrees Celsius.
Okay.
But mixtures tend to melt over a range of temperatures, like chocolate.
Yeah, it kind of gets soft.
Exactly. Gradually loses its shape.
Yeah, okay.
So this observable difference becomes a practical way for students to understand this basic concept.
That's something they can actually see.
Exactly.
That experience.
It's tangible.
Yeah.
Okay, so once we have this idea of a pure substance, how do we introduce particles?
Yeah, like where do we go from there?
So the model starts with these core ideas,
okay,
which have been tested with kids around 9 or 10 years old.
Okay.
First, a substance is made up of tiny, identical particles. Second, particles of different substances have different abilities to hold on to each other.
Okay.
Third, these particles are always moving.
Okay.
And have energy of movement. And finally, heating a substance increases this energy.
Okay.
Now, at this stage, the actual nature of these particles...
Like if they're atoms or whatever?
Yeah, whether they're atoms or molecules isn't specified.
Got it.
We're just focusing on the behavior of these generic substance particles.
Okay, so how does this model explain melting then?
So melting is understood as the particles gaining enough energy to overcome that hold that they have on each other. Okay. So they can move around more freely. Yeah. Which is what we see as a liquid. Right. But they still stay pretty close together. Okay. And this is a key difference from the traditional model. Okay. It avoids the idea that solids and liquids are totally different types of matter. Okay. Now, the term hold is used here instead of a more complex term like intermolecular forces.
Or attraction.
Right, because it's a simpler concept.
Okay.
And it sets the stage for a better understanding of bonding later on.
Okay, like a more gradual introduction.
Exactly.
So what about gases?
Okay, so if you keep heating the liquid, the particles gain more and more energy. Right. They move around a lot.
Yeah.
Eventually, they have enough energy to completely overcome that hold, and they spread out to fill the container.
Yeah.
That's the gas state.
So you can see this in that experiment with the syringe.
Exactly like the hot gas syringe experiment.
So you heat up the liquid.
Right.
And then
you heat it up.
It expands and fills the whole syringe.
And it becomes a much larger volume of gas.
Yeah.
And the substance-based model says that even gases are still substances. It's just that their ability to hold on
to each other is really weak.
Is very weak.
Okay, so it's all about this interplay between the energy and that hold.
Right.
So let's take some everyday things.
Okay.
And look at them through this substance-based lens.
Yeah, I like it.
So melting.
Okay.
Why do things melt at different temperatures?
So in this model, melting isn't just a solid becoming a liquid.
Right.
It's the particles.
Yeah.
Gaining enough energy to break free from that hold that keeps them in that fixed arrangement.
Okay.
And different substances have different strengths of this hold.
Okay.
So substances with a stronger hold need more energy.
Okay.
And therefore a higher temperature to melt.
So like iron versus ice.
Exactly. Yeah. Iron melts at a much higher temperature than ice.
Okay.
Because its particles have a stronger hold.
That's a really cool way to think about it.
Right.
What about dissolving? Okay. Like when I put sugar in my tea.
So dissolving is when the particles of the solvent,
sugar.
Yes, the sugar in this case,
right,
separate from each other.
Okay.
And mix with the particles of the solvent.
The tea, the water.
Right, which is mostly water.
Okay.
And the key here is that this hold applies mainly to particles of the same substance.
Okay.
Now, this model doesn't fully explain why some substances dissolve better in others.
Okay.
That gets into more complicated things like intermolecular forces. Yeah. But it does give us a foundation for understanding that dissolving is about particles mixing. Yeah. From at least two different substances.
So the sugar isn't just disappearing.
Right. The sugar particles aren't vanishing.
They're just spreading out.
They're spreading out and interacting with the water.
Right. Okay, what about boiling?
Okay, so boiling is presented as a collective phenomenon.
Okay.
So when a liquid is heated to its boiling point, lots of its highest energy particles gain enough energy to overcome the hold and form bubbles of the same substance.
So like water vapor.
Exactly. Water vapor in the case of water. Right. So it's a big escape of particles.
Yeah.
Transitioning to gas.
Of the same substance.
Of that same substance. Yeah. And it happens throughout the liquid.
Not just at the surface.
No, not just at the surface.
Right.
It's different from evaporation.
Yeah. So how is it different from evaporation?
This is where the idea of energy distribution is important.
Okay.
Even at temperatures below boiling, some particles...
In the liquid.
Yeah, in the liquid will naturally have more energy than average. Yep. So evaporation happens when these high-energy particles at the surface gain enough energy to escape into the air.
Okay.
They can also be knocked away by air particles.
Okay.
Now, this is an individual process. It happens particle by particle, mainly at the surface.
And boiling is like a group activity.
Exactly. Boiling is a collective event happening throughout the liquid.
So why doesn't a puddle just disappear then?
Well, there's a constant exchange of energy. Some water vapor in the air will lose energy and rejoin the liquid.
So it's a balance.
It's a dynamic balance.
Okay. So the air is really important for evaporation.
It plays a big role.
More than we might think.
Yeah, more than the standard model suggests.
What about condensation then?
Okay, so condensation.
Like dew forming on grass?
Yeah, or those droplets on your cold glass of lemonade.
Yeah.
Happens when the water vapor in the air loses energy as it cools down.
Okay.
And when they lose enough energy...
The particles.
Yeah, the water particles, they can't overcome the bumping and jostling from the air particles.
Right.
So they start to cluster together.
And form droplets.
Exactly, forming those liquid droplets.
This model really does paint a much clearer picture.
It does. It's a more dynamic picture.
Of all this stuff.
Yeah.
Now, the research you sent.
Yes.
It looked at how 9 and 10-year-olds responded to this.
That's right. They had some studies.
What did they find?
So the studies were small, but they had some really encouraging findings.
What were they?
They found that these young students were generally pretty engaged.
With the substance-based model?
Yes, with the substance-based model.
That's really cool.
Yeah.
What else?
Well, a good number of them were actually able to apply these particle ideas to explain things like melting, boiling evaporation, dissolving condensation.
Wow.
So they seem to grasp this idea that particles make up the substance, and they use changes in the arrangement and movement
of the particles.
Yes, of the particles.
To explain changes of state.
Exactly.
That's really promising.
Yeah, it is.
It sounds like maybe these ideas aren't too difficult for younger kids.
Maybe not as difficult as we thought.
Were there any parts they struggled with?
Yeah, there were a few interesting things.
Okay, like what?
So when explaining melting, they understood the hold being overcome. Okay. But many thought the hold just weakened. Yeah.
As it got hotter.
Yeah, as the temperature increased.
Instead of it being a change in the balance between the hold and the energy.
Right. It's more about a shift in that balance.
Yeah.
Also, for evaporation, the students preferred the idea of air particles knocking away water particles. Okay. More than focusing on just energy distribution.
Interesting.
And for condensation, explaining it as air particles losing energy worked really well for them.
So they were building their own mental model. Because that made sense to them.
Right.
Even if it wasn't perfect.
It was a starting point.
Yeah, the starting point.
Right.
So what are the big implications then?
So the research really argues that the traditional model...
The solids, liquid, gases one.
Yeah, that one might actually be making it harder to understand.
Particle theory.
Particle theory. Yeah. And by shifting our focus to substance, we might be offering a more accurate and a more intuitive way...
To learn about it.
Yes, to learn about the fundamental building blocks of the world.
It feels like this could really help.
Yeah.
With more advanced chemistry later on.
Absolutely.
If you start with this...
If you start with this substance-based framework, it could make a big difference.
So the researchers are saying we should introduce this earlier.
They're suggesting that,
Maybe even in elementary school.
Potentially.
Interesting.
And, you know, it aligns with more and more research that shows elementary students can handle more abstract ideas
than we thought they could.
Exactly.
But we need more research.
We definitely need more research.
To compare the two approaches.
Yes, to directly compare them.
It's amazing how just changing our perspective can make such a big difference.
It's pretty powerful.
So as we wrap up this deep dive, what's the main takeaway about this substance-based model?
So the core message is this.
Okay.
By focusing on substances and their particles, rather than just the states we see, we can build a better foundation.
For understanding matter.
Exactly, for understanding the world around us.
So it's about recognizing the underlying unity of matter.
Yes.
Not separating it too early.
Not creating those artificial divisions.
Yeah, that's really powerful.
It is.
So for you listening out there, I want you to think about everyday stuff. Like humidity. How chocolate melts. Or even boiling water.
Right.
How does this new perspective change how you understand what's happening?
At that tiny level.
At the level of particles.
Yeah.
What new questions does it raise for you?
That's a great question for listeners to think about.
About the nature of matter.
Yeah.
I encourage you to check out the research.
Yeah, definitely.
And keep exploring this stuff.
It's fascinating.
Thanks for joining us.
Thanks for having me.